Okay, so here's our formula for the apparent brightness. Little b is the apparent brightness, right? L is the star's out luminosity, right? And then d is how far away the star is, right? And the idea of this is that brightness is, of course, this is where sort of physics leaves off, and then we're going to go into astronomy formulas, right? But the idea here is the watts per square meter is the power over the area, right? How much power per unit area that you receive from that star. For the sun, it's roughly about 1400, at our distance from the sun, about 1400 watts per square meter. That's the solar constant, which isn't exactly constant. It varies with sunspot cycles and other things, right? But for a distant star, this is actually very, very small. You can't actually sunbathe under stars at night, right? And then the reason why it's 4 pi d squared, and of all, pretty much all inverse square things happen, is that, well, if you look at a sphere like this, right, as you go out, if you go out 1 unit, you've got 1 unit of area. If you go out 2 distances, right, then you actually have 4 units of area, right? And if you go out 3, whatever these units are out, right, you actually end up with 9, right? So the idea is that these watts are being spread out over a square meter, and the square meter is the sphere where you are, right? And the sphere where you are has this area 4 pi d squared, where d is how far you are from the object. And that's why, by the way, the Coulombic force is inverse square, because the little particles that mediate that force spread out over a sphere, and the same is true for magnetism and things like that. Okay, for gravity as well. Okay, so let's go ahead and put this one in your notes, right? The sun puts out that many watts of power. We are that far from it, and so what is the apparent brightness of the sun from Earth? Well, B is how many watts you have divided by how many square meters of area there is at a sphere at your distance, right? So 4 pi d squared, right? So that's going to be 3.87 times 10 to the 26th watts, and then it's spread out over a sphere that is, an astronomical unit in size, right? So it's 4 pi times 1.50 10 to the 11th squared, and then that is 3.87 e26 divided by, and then you got to put the whole denominator in parentheses with these calculators, unless you've got that fancy upgraded TI-84 stuff. Okay, so divided by 4 times pi times 1.5 e11. I'm going to square that and then go like that. Okay, here we go. Are we ready for this greatness? I'm getting 1368.7 watts per square meter. So yeah, the sun is, that's pretty bright. Definitely the brightest object in the sky. Okay, and then with 3 sig figs, we'd have to round it to that. Do we have 3? We do. All right, I'm going to do another example. Again, you got this one in your notes. You'd be good enough to go tomorrow, or whenever it is we do these in class. But I'm going to do another example if you want. If you don't want to watch this example, I just go to the next video. Okay, another star has a luminosity of that many watts. We measure an apparent brightness of that many watts per square meter, so how far are we from it? So now, and this, by the way, this is the crux of a lot of our distance measurements, right? Is if we know how bright it really is, somehow if we can figure that out, how bright it appears, we can use the distance brightness relationship. Right, so B is equal to L divided by 4 pi d squared. So we want to find D, right? So let's see, D squared is going to be L divided by 4 pi B, because you can just switch things in the numerator there to the denominator there, right? And then we can square root that, right? And then we're good, right? So let's see, 3.2 10 to the 26th watts. Okay. And then that's divided by 4 times pi times, what is it, 1.4? 10 to the minus 9th. meters. Oops, that's watts per square meter, right? Okay, so let's see. Is that going to be meters? It will be, because watts will cancel watts. We'll have 1 over meters squared. The world will be a good place. Okay, so let's see. Parenthesis, 3.2 e to the 26th divided by beginning of the numerator, parenthesis, 4 times pi times 1.4 e minus 9. Right parenthesis that ends the denominator, right parenthesis that ends this expression, raised to the 0.5. That's going to square root it, right? I got 1.35, I'll say, right, times 10 to the 17th meters, right? So that is, if I figure out that in astronomical units, that's divided by 1.5 e to the 11th, right? That's 1, 2, 3, 4, 5. It's about 9 times 10 to the 5th. 9 times 10 to the 5th astronomical units. That's pretty far away. Ta-da. Yay.